You are not next to leading log.
Welcome back to the second morning section. So the first talk of the section is the Saclay approach to jet quenching, factorization, and the role of the color coherence given by Paul. Yeah, please go ahead.
All right. So good morning, everyone. And thanks a lot for the invitation to give this talk. So I've been asked to discuss the factorization in jet quenching physics in particular. And so this work is in collaboration with Edmond, Hal, and Gregory. And so it dates back since a couple of years now. So I apologize if you have already seen some of the slides today. Right, so I like starting with this. How does okay, yeah. So I like starting with this kind of like picture which compares the situation in PP, which was nicely explained by Alba in the previous talk, and what we have in heavy-ion collisions. So basically, in PP, we have this scale. I mean, this scale here from the hard process down to the non-perturbative scales, which gives large logarithms, which needs to be resummed to all orders. And but you see, the situation is simpler because we don't have any intermediate scales that we have in comparison in the dense QCD environment of heavy-ion collisions. So in particular, at some point between this hard scale here and the non-perturbative scale, the jet will encounter semi-hard scale related to the quenching parameter and the system size, and also at in the infrared regime, some other scale like the temperature, where the hydrodynamical evolutions also needs to be included. So yeah, in general, jets are sensitive to a broad range of scales, and the question in heavy-ion, of course, is to try to understand how to organize all the physical mechanisms that the jet will encounter while evolving in this dense background. All right, so just to summarize before going into the details, so this Saclay approach, as called by the organizer, in a nutshell, so it's based basically on the most simple approximation in PQCD, which is this double logarithmic limit. So it's in a sense, a more drastic approximation that the next to leading log Barton showers that people in the PP community and E plus minus want to build, because I guess in the heavy-ion case, the system is more complicated. So it's, I mean, we have to go step by step, and the first step is to control the double logs in the Barton shower. And this double logarithmic picture of jet evolution will, brings a very nice feature, which is also related to the talk by Varun yesterday. This feature is a factorization between the early vacuum-like cascades, leading twist effects, and medium-induced emissions. And this approach also includes recent developments related to the role of color and color coherence and decoherence effects. And I will give you more details about that later. All right, so let me start with this basic double log picture of jet evolution in the vacuum first. So here you can recognize basically what Alba was showing. This is the soft and collinear limit of the n+1 matrix element which factorize from the n particle projection cross-section. And it has this very well-known double logarithmic enhancement both in the soft and collinear regime. So it's also interesting for parametric estimations to build a formation time for the given emission which is associated with the spectrum, which goes like 1 over omega times theta square, as you all may know. And in order to account for the correct logarithmic structure of this of the jets, while emissions are emitted according to the spectrum, we need to impose an angular ordering constraint, which basically the consequence of the soft structure of, the large angle soft gluon structure. So yeah, in this soft and collinear limits, you can see a jet as a Markovian process, iteration of emission softer and softer, more collinear along the emission, along the tree. And you can also represent such a Markovian process on a Lund plane, which is here represented as a function of angle and energy. And you basically, there is a one-to-one mapping between this tree here and this phase space in which each emission is recorded. Okay, so this is a picture in the vacuum. Of course, in the vacuum, we can do much better than that. And again, I refer you to Alba's talk if you want to include higher order corrections. But at least that's a common ground to try to understand what are the modifications of this simple picture in a case of a dense medium. So I will mainly discuss the dense QCD medium case. So in the dilute limit, we can discuss that, of course, after or offline, but here I will mainly assume that the medium is dense enough so that there is a need to account for multiple source scatterings. So we need to resum these all twist corrections. And the interaction between the hard partons inside the jet and the plasma will be described as an effective parameter Q hat, which is basically related to the average transverse momentum squared acquired by the hard parton while propagating through the medium over distant time delta t. So this defines the quenching parameter. So of course, it's a quantity which depends on also some the scales of say some art scale, but in this multiple source scattering approximation, I will basically consider it as a constant in this talk. So I will, in the outlook, I will comment on that, on the possible dependence of Q hat as a function of KT squared. All right, so in order to understand the modification of the vacuum phase space that I've discussed in the previous slide, we need to understand a bit qualitatively how an in-medium parton is affected by the presence of this dense medium. And the qualitative statement that we can make relies on the comparison between the formation time, vacuum-like formation time of the soft and collinear radiation inside the medium, and the typical KT that this parton can acquire over this formation time. And if you just, very naively, if you just plug in this expression, the formation time here, you see that necessarily inside the medium, during the formation time of the parton, the transverse momentum squared has to be larger than Q hat times this formation times, right? So it's just a consequence. So this relation is just a consequence of plugging the value of the formation times TF inside the relation between KT squared, the average KT squared, and the formation, and the time of propagation. So this provides a lower bound. So KT squared has to be larger than Q hat times TF. And in terms of omega, for instance, the energy of the emission, it goes like square root of Q hat times omega. So you can draw this line on the Lund plane, and it's basically this red line that will continue down to this scale here, which is not represented in this phase space, because basically you have another criterion which is related to the finite length of the medium. So typically the jet has a typical path length, and below, when the formation time is smaller than L, we expect the cascade to behave exactly as in the vacuum, because there is no dense medium anymore. So you see, just because of these two constraints, square root of Q hat omega here in red and the TF equal L line, we have some here region which clearly separates what happens inside the medium to what happens outside. And from this basic reasoning, we expect at the LA no radiation inside this region here. So this is a question which is intriguing. It's an intriguing feature of this qualitative statement, but actually one can try to understand maybe more mathematically where it comes from. So first, I would like to emphasize that this constraint here, the red line, and which bounds the vacuum-like emission inside the medium, is a leading twist effect in the evolution. But it's a leading twist effect. The boundary is induced by multiple source scattering. So it's a bit, there is an interplay between the all twist corrections coming from multiple interactions between the hard parton and the medium, and the development of the cascade triggered by the high virtuality of the hard process. And in terms of maybe more PQCD-based computations, if you take the spectrum, say for having a quark going to quark and gluon in a very big medium and dense, you can actually see this boundary emerging from the computation, because you can decompose the spectrum as a soft and singular piece with a soft and collinear enhancement in the infrared, with a constraint which is basically coming from competing phases in the in-medium effective propagators that have been discussed yesterday in this BDM-PSD approach. And the other piece is non-singular, and we shouldn't be resummed because there is no such soft and collinear enhancement. So this is in the L going to infinity limit, so which provides this line. And again, of course, if you want to go beyond this limit and include finite length effects, you would see that the spectrum actually behaves a bit differently, in the sense that you will also see vacuum-like emissions with formation time larger than L, of course, but also kind of vacuum-like emissions triggered by the interactions between the hard parton and the medium, because the medium can get kicks of order to the hard guy of order kT squared, given by this scale here, and because of this kick, the outgoing particle can again radiate according to this branch-Pralung law. But in a leading twist approximation, only this kind of emissions, either in this red region or in the blue region, should be iterated. All right, so this is for the phase space, and basically this spectrum here is the analogous of the factorized cross sections that Alba discussed in the soft and collinear limit. So in a sense, to answer your question, there is a factorization between matrix elements and n and 2n plus 1 matrix elements, and in the dense and large system size limit, it's given by this expression here. So now let me discuss a bit the role of color coherence and color decoherence, because what I've discussed so far is just the spectrum of the emission spectrum of an initial colored object like a quark or a gluon. So in principle, and in particular, if we want to understand the soft radiation pattern, we need to also look at how soft gluon radiation are distributed if you start with a dipole. And in this case, I will discuss a case of a color singlet dipole with a given opening angle theta bar. And from many studies, already 10 years ago, it is known that because of the multiple interactions between the hard legs of this dipole and the scattering centers of the medium, the color coherence of this object in the vacuum, which leads to the angular ordering property, can break down, and emissions, in principle, soft emission with an angle larger than the opening angle of the dipole could be allowed. And this is a problem, because we know that the full DLA picture of jet evolution in the vacuum is based on this angular ordering property. So if such emission were allowed inside this domain, we would need to change the way we build, for instance, Monte Carlo parton showers inside the medium. But the nice feature of this scale, this time scale here, after which the antenna has lost this color coherence, is that it's also, you can just, again, by playing with these scales and this boundary here inside the red region, by playing with this scale, you see that, in fact, this vacuum-like cascade inside the medium happens so fast that they don't have the time to decohere. And this very fact implies that you shouldn't expect angular ordering breaking inside the red region. And gluon cascades should be angular order as in the vacuum, at least in this double arithmetic approximation. So it's a very good news because it means that we can apply basically the same techniques as in the vacuum for the in-medium cascade, and maybe extend that to I mean beyond the double arithmetic approximation and beyond the double arithmetic limit to increase the precision of the Parton shower. All right, so this was for the emissions inside the region, inside the medium, in the red region of the phase space. Of course, we also know that for very small antenna, that you expect the medium not to be able to resolve this antenna, and this is, in terms of scales. This resolution scale of the medium is an angular scale which is precisely related to this decoherence time when we set the opening angle of the dipole to be equal to L. Right. So if the opening angle is larger than theta c, after the propagation of the dipole through the entire medium, the first emission outside can have any angle. So this is a consequence of the decoherence of large angle dipoles while propagating through the medium. And this kind of large angle soft emissions outside the medium, I have a phenomenological impact, and I will discuss that a bit in some for the fragmentation function, for instance. All right, so this is basically what I had to say for vacuum-like emissions. And of course, when you want to, so at this stage, there is no energy loss because everything is angular ordered except for this first emission outside the medium, which is soft. So in principle, shouldn't contribute that much to the energy loss by the jet. So if you want to agree with data and where we clearly see jet quenching, you need to include medium-induced emission in this picture, but it's beyond the LA formally. And the way to include it is precisely to rely on this factorization, because we know that these medium-induced emissions, which are the dominant contributions to the large angular energy loss of the jet, have a KT squared which precisely satisfy the lower bound of the in-medium phase space. So the KT squared is basically given by the Q hat times TF, which means that the formation times is square root of omega divided by Q hat. So the picture is the following. So we have a bunch of vacuum-like emissions with an angle larger than theta c, which can radiate any kind of medium-induced emissions. And then since the spectrum has also divergence in the soft limit, but no collinear divergence, just a soft divergence, you should iterate also the spectrum to account for the multiple branching regime in which the probability of emissions of this spectrum becomes of order 1. So it's another Markovian process which is now ordered in time, really in the light point time along the propagation of the initial hard Parton which triggers the first medium-induced emission. And there is no angular ordering constraint for that, and that explains why large angle energy loss is possible in this framework. So this is a summary of this factorized picture. So we have in this Lund plane the similar typical cascades that can happen inside the medium. So first, an angular order cascade inside the red region, inside medium region, which ends at this for this emission here, for instance. Then this emission can, while crossing this virtual region, can trigger a bunch of medium-induced emission, which are iterated according to this Markovian process ordered in time, and which has also been discussed, for instance, by Suvik in the first talk of the session. And then after that, again, a vacuum-like cascade outside. And because of this decoherence effect and this anti-angular ordering property, some cascades may behave like that with one emission violating the angular ordering property. All right, so just to flash out some recent developments, which includes the longitudinal expansion, because we have seen a couple of talks about the time-dependent QAT applied to the problem of medium-induced emissions mainly. So here I will focus on how to extend this phase space basically to the case of a Birken expanding medium. So it's basically the same argument. So you can also see that from more formal calculations, say, but in principle, you can also infer the boundary, the red boundary, just by saying again that the KT squared of any emission inside the medium is bounded by the typical the integral of QAT of T along, between during the duration of the emission of the gluon inside the medium. So TF here is again related to omega and theta. And if you do this integration, so in the case of an ideal Birken expansion, you get a log, which was not the case for a static medium. And that leading log, we can basically neglect all this log of slowly varying function, and the boundary becomes omega times theta, which is basically the KT, larger than this scale here. So I think it's better to see the modification in terms of phase space. So if you compare the picture in the static case, the Lund plane, right, was the in-medium boundary was given by this dotted dashed line here. In the case of an ideal expanding medium, to leading log accuracy, it's given by this red line. So not a big modification, but at least formally at DLA, it's a double log effect actually, because it's an area in this Lund plane. All right, and just for phenomenology, in the case for the medium-induced cascade, since we are working only in this soft limit in which we focus on the singular part of the BDM-PSD spectrum, the process can be seen as a quasi-local process of medium-induced emission along the path length of the jet. And as we have seen, under this approximation, we can basically change the definition of the time, and we have an equivalent, we can basically map the expanding medium case to a static medium just by using this change of variable inside the cascade. So this has been discussed already, so I will not spend too much time on that. And yeah, for the RAA, there is a very small effect actually of there is a very small effect of this expanding. If you compare the static equivalent static scenario with the expanding case, in which the scaling property is violated only by the vacuum phase space, you see that it's a very mild modification, in fact, even if it's again formally a double log effect. All right, so yeah, in the last couple of minutes, I'm going to just flash some interesting observables that have been measured by Alice and Atlas in this. I won't define the observable because we have already seen. We already had a nice talk about that yesterday, and I guess in the coming days as well. So, but this is basically the θg distribution measured in heavy collisions and compared to PP. And what I want to highlight is the fact that this modification of the phase space here, which introduces also this coherence angle, has an important effect in the sense that in our picture it explains why we have a strong θg dependence of the RAA, or equivalently a strong θg dependence of the ratio of the θg distribution in lead compared to PP. And the scales at which we have a transition between, say, the inclusive RAA and the RAA for larger values of θg is given by the θc angle. It's driven mainly by the θc angle. Of course, there are other effects like, as we have seen, the narrowing of the distribution due to the fact that at larger PT, jets tend to be narrower. But we see that for instance, in this plot, or if we give parametric estimates of the θc angle, the transition scale is given by θc. So in order to disentangle the effects that we have discussed yesterday in the discussion session, we will need to, I guess, look at other observables which are less sensitive to these bias effects. But yeah, at least in this very simple calculation, the theta C angle drives the modification of the distribution or the modification of the RAA as a function of theta G, as you can see in this plot. I was also, so yeah, this is basically what I have explained. So there is also a phenomenological implication of the color decoherence, this anti-angular ordered emissions along the cascades. And very briefly, if you again look at the fragmentation function, we expect an increase of soft radiations inside the jets from decoherent soft gluon radiations emitted outside the medium. And also, of course, we have many effects that contribute in this soft domain. So this is one of them. You have also in this calculation the effect of soft intrajet medium-induced emissions. Many other effects can, I mean, the response to the jet can also, we know that very well, can also trigger additional soft gluon radiations. But this is something which which also appears in this picture. And to conclude, so we have this picture which can be improved on both sides, both in the vacuum-like side and in the medium-induced side. So for the vacuum-like, okay, I won't spend too much time because again, Alba gave tried to make this comparison between vacuum and medium medium cascades. But the interest, for instance, with working indeed with dipole, that in our framework right now we cannot describe the dye-data symmetry or the gamma jet X gamma jet fraction, for instance, because we miss, for instance, initial state radiation, and this has effects. I mean, even in PP, we wouldn't be able to describe these observables. Also, we are missing the geometry, which is an important aspect of the dye-data symmetry. And on the medium-induced side, we have seen a lot of exciting developments, both in terms of the description of the single emission spectrum, in terms of how to iterate the spectrum, both in terms of X and KT dependence, also the need to account for rare R scatterings, because so far what I showed today is mainly based on the multiple scattering approximation. So all these developments, I believe, could be included in this kind of picture. So it can be done either in our framework or any other, but at least it's a common, I mean, to my from my point of view, it's a nice common ground to start including refinements in every domain of the jet medium interaction and jet propagation inside the plasma. All right, so that's basically it. So thank you very much.
Paul, I always have a hard time understanding this Vito region that you put in your Monte Carlo. So what I don't quite understand is that so this estimate of the lower bound for the KT is like assuming that your particles that you're emitting are like constantly gaining KT while they are propagating through a medium. So more or less, right? But the vacuum-like emissions that so you concentrate in the vacuum-like emissions because is the part that has the double log. And the part that has the double log is the vacuum part only, is the part that doesn't have any scatterings with the medium. So I don't really get why you have that Vito region if you're considering inside is just independent of the medium, is just vacuum, the original shower that you have. So if you go to the slide, or yeah, right there. So you separate this as this part and the non-singular, but the other part is also non-singular. I mean, it has a 1 over KT T square, but but the theta function means that you never reach that that singularity.
Right, but when you integrate the spectrum up to the art scale of the problem, is precisely the medium the medium physics is more complicated because you have intermediate scales. So if you want to count the log, you want to account both for logs of the art scale divided by the non-partitive scale, as in PP, but also logs of the art scale divided by the medium intermediate scales, which here is square root of Q times omega. So if you integrate this indeed non-singular piece for a vacuum physicist, in our case, it gives a log of, say, Q divided by square root of Q at omega. So if this scale is indeed much smaller than Q, say, think about a very large PT jet, this is a kind of log that we would like to resum to all orders.
Yes. Okay, but I guess so. In the same direction, what I find a little bit puzzling is that this relation of saying that you're gaining some transverse momenta that is proportional to how far you go, it's an average picture.
Right.
But you're doing an event generator. So,
right. So since I know that this kind of parametric estimates cannot be for maybe formal physicists, but not so convincing. I really think that if you again take your computation, for instance, and take the infinite medium size limit and focus, so you have time integration over the emission time in the amplitude and compressed conjugate amplitude. If you focus on the domain in which the difference between these two times are much smaller than this square root divided by omega times Q hat, you can see that because you will get this result, and you will see that the in-medium propagator is basically reduces to the vacuum propagator, and that gives you precisely the vacuum-like spectrum, Bremsstrahlung-like spectrum. So I think you can see that also in the math if you want.
Okay, so just one quick thing, a quick question about this. So in your Monte Carlo, you have two things, right? You have the Vito region and the one emission that doesn't respect the angular order. Have you tried to not use the Vito region, so to do the same Monte Carlo, but doing
right.
And the results are very different, or
no, because with since as I said, you have some kind of effective parameter, you can always basically change the value of Q hat to again, because what drives the RAA, for instance, is the fact that you have a large phase space for in-medium vacuum-like emissions, which may in the end lose some energy out of the jet cone. So even if the phase space for in-medium-like emissions is larger, you can still, by rescaling Q hat by some factor, you can still get the RAA correct. The question is, again, we believe that in terms of logarithmic resummation, we would overestimate the in-medium multiplicity of certain collinear particles if we don't include this constraint.
It's a question on June Soren.
Yeah, hi, Paul. I have two questions actually. The first one is precisely on this slide, actually, if you want. So if I understand this, I'm supposed to read this kind of as a sequence in time, also how things happen, right? You first have sort of the vacuum shower inside the medium, then you have medium-induced emissions, and then you have the evolution outside the medium. So my question is, when you do medium-induced emission, who emits actually, and it's sort of, do you know how to deal with sort of the medium resolving the vacuum-like emissions as a single source or as multiple sources? How is
right? So it's multiple sources. So basically, it's factorized. So you see that as a convolution between three processes. And the first process is the Barton shower inside this phase space. And at the end, we collect all the patterns that we have. So it's, basically generating this shower is like generating a vacuum shower with this boundary, with a modified boundary. Instead of having just this KT cutoff, we have this more involved red and blue line here. And all these patterns then trigger a bunch of medium-induced emissions, which are also iterated, but according to another evolution variable.
Yeah, okay. But so the case where, I mean, right, because if you have a very narrow vacuum splitting, right, then in principle, you know, it's possible that the medium only sees the net Collar charge of the splitting and not the two individual.
Right, but this, I mean,
this is already, so this is already taken account by your phase-space constraints, so to say.
Right, yeah, because you see, even if it's collinear, it's collinear physics, since the theta c angle is quite small, it is still larger than theta c. So this the non-resolved splitting are below this blue line.
Okay, I see. Okay, I see. Thanks. And then I mean, the second question is, right. So I mean, this is all very nice, right? And you can sort of easily do this estimates and get these regions if you use just sort of this Gaussian random walk picture for momentum broadening, right? So, I mean, so you mentioned at the end, like, you know, that you want to improve on the way that you treat jet medium interactions and so forth. So is this obvious how to do this, or is this going to be really hard?
I mean,
do you know how to do it in principle to just work with the generic collisional kernel? Right.
So for the medium cascade, you can. I mean, we know how to include, like, to go beyond this diffusion approximation, either by solving analytically the evolution equation, this kinetic equation.
Yeah, sure. Yeah.
Right. You can also do that using Monte Carlo methods. So this can be done, and I was referring to that in my outlook. But for the Haas scatterings trigger, which can modify the vacuum-like structure of the cascade, honestly, I wouldn't. I mean, right now I don't know how to do it in a consistent way. How to include also the very rare cases in which one Haas scatterings, which can also change the virtuality of your parton quite a bit, and that would then lead to another cascade, which would in fact interfere with the initial high virtuality of the Haas process. Yeah, that I
okay. Thanks.
Oh, hi, Paul. Hi. I'm just wondering, when the sort of scale when you get into like outside the medium, which essentially depends on the propagation time, right? So during that time, when you reach that point, what is actually the scale that start responsible for the vacuum shower again, the typical scale, like Q squared?
Oh, so
I assume it's probably around Q hat.
Right. So I mean, right at the end of the medium shower, after then evolving again inside the medium, the typical KT is given by I think it's in fact given by QS or square root of Q hat omega. So basically, it's along this line.
Along that. I assume it's like Q hat.
Yes.
And that if you by the time it depends on how long that the medium tag is like if you travel very long time, by that time the medium is not really dense anymore. That Q hat is not going to be very large, right?
Right, but
so in this case, I'm just curious, what is the total effect of outside the medium vacuum-like radiation in your simulation?
Right, so I'm not sure. So because there are two things, right? So first,
just look at your tree, right? Just look at your tree. I mean, outside the medium. I mean, look at the diagram. By that point, what is the typical Q square, right? And I assume it's on the order of like some Q hat, time scale.
Right, but even in the expanding case, the cascade basically accumulates some transverse momentum, which is integrated over the full path length. So it's you can estimate that it's not it's a prefactor times QS in the static case, I guess, if I'm not mistaken.
Yeah, are you saying that is depends on the integrated Q hat along the path length?
Yes, I think so. Yeah.
Okay.
But these emissions outside, they are not really related to. They're really coming from the high virtuality of the initial guy, not necessarily because since the medium can gives kicks. Gives a virtuality to the pattern. You have somehow competitive Bremsstrahlung effects between the Bremsstrahlung triggered by the high virtuality and the one triggered by the medium scatterings. And those we are not including the latter are not included in this picture. It's purely.
We can discuss it offline. I think there might be some other scale responsible instead of you integrated,
Yeah, sure.
Suppose you have like a neutron star, like long length. Definitely when you get out, if you have like QGP like a neutron star, from the beginning to the end, and by the time you get out of the neutron star, I'm not quite sure the radiation scale is determined by the whole path length of the neutron star anymore.
Right. I see what you mean. So yeah, okay. Yeah, but we can discuss that.
Okay, so let's thank the speaker again. We'll move to